Cool. So welcome everyone to the Symmetry seminar. This is actually the last one before we take a break. There's various workshops, one at the GGI in Florence and then something in Paris. But it's a great pleasure to have Tom Hartman now from Stanford who'll tell us about conformal Turaev-Viro theory and 3D gravity. So please take it away, Tom.
All right, thanks very much. So can you see the meeting is being recorded thing blocking the slide, or is that just me that sees that?
I think that's just
I
you.
don't see
We
anything.
don't
You
see
don't see
that.
it. Okay, that's fine if it's just for me. Okay, great. So um, I'm gonna start with some introduction. I'll go through the introduction to this topic fairly quickly so that we can get to the new results, but feel free to stop me as we go here if I'm going too fast. And I just want to introduce some of the background of where this whole subject is right now. So the ADS-CFT correspondence in its original form says that two specific quantum theories are equal, that a specific string theory, when you include the full non-perturbative UV-complete theory, if you're able to define it, is exactly dual to a particular conformal field theory. But since 2019 or so, we've accumulated a lot of evidence for another version of the duality, which is coarse-grained or ensemble averaged. And in the ensemble average version of the duality, the string theory is replaced by a low energy effective theory. So general relativity, maybe plus some particles or matter. And on the CFT side, a particular CFT is replaced by some sort of ensemble average over CFTs. And we don't know exactly what this equation means, and that's what we're exploring. But that's the picture that's coming out. If it was just this equation, this would be sort of obvious. If we could just take the low energy limit of the ordinary ADS CFT correspondence, this would be an obvious low energy sector. But what makes this equation interesting is the space-time wormholes that you can study using this equation. So space-time wormholes are these connected geometries that have several asymptotic ADS boundaries. And the reason that those make this ensemble average version non-trivial is, well, the connected part of this amplitude should be exactly zero in string theory because it's just a product of a bunch of CFTs, so a product of a bunch of string theories, it should be exactly zero. But it's non-zero in general relativity. Um, if you had asked 2 decades ago, then we would probably have said that non-zero answer in general relativity is just nonsense and it should be discarded. It's going to be canceled in the UV. But the conjecture of the ensemble average duality is that this non-zero answer that you get in general relativity is actually useful in telling you something about the microscopic theory, and in particular, that the multi-boundary topologies are telling you the statistics of the conformal field theories in this ensemble. So that's the meaning of the right-hand side, is that when you calculate these amplitudes on space-time wormholes, you're learning about the CFT statistics. Now, in 4 or more dimensions, gravity is not renormalizable, so this can only make sense. This ensemble average version of the duality, which has general relativity on one side, can only make sense as a low energy approximation. But in 2-dimensional gravity, and plausibly also, we believe, in 3-dimensional gravity, there is a precise duality. So
Tom, I think I missed something. Are you saying the ensemble average applies to the string theory or to the general relativity? The duality.
I'm saying,
Does
well, the duality is between the low energy in the bulk, we just take the low energy effective theory. Sorry, my screen has done something funny here. Is it still looking okay to you?
no.
No, so I think it's now just showing some small part. Yep, now it's better.
Okay, no,
That's better. So
my
could
monitor
you go
decided
back
to come.
one slide? So
Yeah,
the the ensemble average conjecture. So you're saying GR is an ensemble average, but
yeah,
not string theory. In other words, you're not modifying the ADS-CFT conjecture for string theory, right?
Not for the full string theory.
Okay.
I think the real
That's
distinction
what
is
I wanted
whether
to
we,
clarify.
yeah, yeah, right. Um, the distinction is not so much between strings and gravity. I think the classical string theory treated as a low energy theory is also an ensemble average. It's more about whether you include the full non-perturbative effects and all the D branes and everything. Um, so in two dimensions, this is where this was first discovered by Sod, Schenker, and Stanford, and the statement is that two-dimensional gravity is equal to random matrix theory. Um, this is an equal sign. It's the topological recursion in the double-scaled matrix theory is exactly the same as the sum over topologies in the gravitational path integral. The situation in three dimensions is a little bit more complicated, but also there appears to be a duality here that relates pure 3D gravity to an average over two-dimensional CFTs. Um, Now, both sides of this, neither side of this equation of the duality in three dimensions is fully understood. That's what we're trying to work towards. Um, but there are many examples and limits where we do understand how to do calculations on both sides, and there's a lot of evidence for this agreement. So on the left-hand side, we have pure gravity. So pure 3D gravity means a theory that's defined by the gravitational path integral. Schematically, that means we need to sum over all topologies and integrate over metrics on each topology with some boundary conditions. On the CFT side, what is a random CFT? Well, the data of a CFT are the spectrum rho and the OP coefficients Ci, J, K, which are the matrix elements of the primary operators. So the observables of an ensemble, a random CFT, are the statistics of these data. The statistics of the rho, products of the Cs, and mixed versions. Ideally, we will find something like random matrix theory that computes all such statistics and agrees with 3D gravity. So far, we don't have that. We don't have the complete analog of random matrix theory for CFT. But what we can do, in the meantime, we can calculate the statistics order by order in various cases using the conformal bootstrap. And there's an iterative procedure to do this where you start with some ansatz for the statistics that solves crossing on average. And then you take that ansatz and you plug it into the crossing equations and you iterate to find corrections. I'm not going to describe more about the bootstrap side of this duality, but I'm gonna focus on the gravity path integral. But on the bootstrap side, there's a CFT procedure that reproduces the gravity results that I'll discuss. So I'll focus on the gravity path integral that calculates these OP statistics that agree with the bootstrap. The leading term, either from from the gravity point of view, is a two-boundary wormhole that was first studied by Maldacena and Maus. It looks something like this picture. So this picture is a three punctured, or it's a sphere with the topology or the geometry is a sphere with three defects times an interval. There are two asymptotic ADS boundaries, and this looks like three particles that are going through a wormhole. So this is a solution of 3D gravity with three defect particles added, and you can calculate the path integral on this geometry and use it to calculate in the CFT the product of two three-point functions. According to this ensemble average duality, we're going to interpret that as the average of the two three-point functions.
What's the
This
expansion,
produces, yeah,
Tom? What's the
sorry.
expansion parameter? What's the dot? What's the plus dot dot dot? What's the expansion parameter?
The expansion parameter, there isn't just one expansion parameter. It's an expansion in the bulk, it's an expansion in topologies. Higher terms um, have e to the minus c times volumes type factors, but it's not just a power series expansion in some parameter. And whether the well, for this particular case, there are no kinematics or anything to worry about. So I think everything is suppressed by e to the minus c. When we look at more complicated cases like 4-point function squareds, then the those volumes depend on kinematics, and it depends on the kinematics which terms are leading and which terms are subleading. This is presumably not a convergent series, but it's organized, at least the terms that we understand are organized in this expansion in three-dimensional topologies. Okay, so this term gives the Gaussian statistics with a variance called C0 that agrees with an earlier bootstrap calculation. I'm going to define normalized OP coefficients with unit variance. Those would be more convenient for where we're headed. Those will be called big C. So big C ijk is just the OP coefficient with unit variance. So that was the Gaussian term. There are also non-Gaussian corrections, like this four-boundary wormhole. In the original approach, these four-boundary wormholes were very difficult to study directly. Um, it's, well, to write down the metric and calculate the action was a difficult problem that we didn't know how to do when we first started studying this. But this problem was solved using Virasoro TQFT. So Virasoro TQFT is related to SL2R Chern-Simons theory, and it gives a way of calculating amplitudes in 3D gravity based on some simple diagrammatic rules for Wilson lines and Chern-Simons. So for example, the two-boundary Malacena-Maus wormhole that we had on the previous slide is this network of three Wilson lines. Sorry, my I don't have a mouse, so I can't point at it. But if you look at that graph, the theta graph with the P1, P2, and P3 on it, that is the Chern-Simons representation of that Malacena-Maus wormhole. We've normalized that to 1, so that's just a choice of normalization for the vertex in this Virasoro TQFT. That gives 1. And then you can study more complicated amplitudes using the rules of the TQFT. And in particular, this four-boundary wormhole, the non-Gaussian, one of the leading non-Gaussian terms, is represented by the tetrahedron graph in Virasoro TQFT. And it evaluates, you can think of this as the overlap of two 4-point conformal blocks. And it evaluates to a Virasoro 6J symbol, which is essentially the fusion kernel for the just the fusion kernel for the 4-point function on the sphere. Many examples now have been calculated both on the Virasoro TQFT side and on the bootstrap side, and matched. One can match the statistics that are obtained from Chern-Simons to the statistics obtained by the bootstrap. So Virasoro TQFT gave us a powerful method to calculate gravity amplitudes and CFT statistics. However, it's not easy to relate it to the metric formalism, which could be desirable for several reasons. One is to construct the semi-classical geometries. If we actually want to know what are the geometries that are contributing and the semi-classical version, we'd like to be able to write down the metric and say what they look like, and that's not easy in the Chern-Simons formalism. Another reason is to study non-hyperbolic topologies. So the direct relationship between gravity and Virasoro TQFT, they're only directly related on hyperbolic topologies where gravity is given by two copies, gravity amplitudes are given by two copies of the Virasoro TQFT. On topologies that don't admit a hyperbolic metric, There's differences in how the two theories treat large diffeomorphisms, and um, so far we don't have a method for calculating the path integral on the off-shell topologies. In the rest of this talk, I'll describe a complementary approach to doing the gravitational path integral that's based on triangulations. This will solve the first problem on the bullet point here, allow us to construct the semi-classical geometries by gluing them together from tetrahedra. So far, it hasn't been used to solve the second problem, but it might also be useful there because this is an approach that's more based on the metric. And in the metric formalism, it's easier to talk about large diffs, and maybe we can use it to approach that problem, but that hasn't been done. The basic idea is the following. Let's look at an example of the kind of complicated looking wormhole that we'd like to be able to calculate. There's going to be some asymptotic ends, which are each Riemann surfaces. And so those are the flares on the two sides. And then there's going to be sorry, one sec. I'm just uh,
Are you okay?
realizing my I'm just realizing my video had
I think
stopped.
yeah, when the screen went funny, it kind
Okay,
of
I don't know.
stopped it.
I'll just bring it back. I think it's back. It's
Yeah,
working
it's
now?
back, yes.
Okay. Yeah.
Yeah,
I
everything
was
looks good.
I was using my hands and realizing that you couldn't see me. Okay, um so there's these two flares on the two sides. Those are asymptotic boundaries. And if those are some boundary conditions, we want to calculate the path integral with those boundaries. Then there are contributions where there are these flares, and then there's some core region with some complicated internal topology.
Tom, before you go on, I mean, I guess you want the flares because you want ADS boundaries, but what's the role of cusps? What if the things are shrinking instead of growing?
That is a good question. So cusps feel like they should have something to do with an insertion of the density of these geometries that I'm describing will calculate the statistics of the CIJKs. A cusp has a torus that looks like a torus that's shrinking. So it feels like that should be related to the density of states factor, maybe the density of states near threshold, where you set since that corresponds to the holonomy for a cusp. But
You
there
can't
isn't
have higher genus cusps. You can't have the higher genus
no
shrinking.
cusps are no cusps
Genus one.
will always be tori.
I say.
But I don't think we really, it feels like it should be a row factor, but I don't think we really understand exactly how that works. There's some proposals for how to include those in the path integral. So to calculate an amplitude like this, we'll take the following steps. First, we're going to split it into the core and the asymptotic ends, the flares. The core will decompose the core into generalized tetrahedra to describe that internal topology in the core region. And then the exact path integral on the core is computed by a novel TQFT, which is the conformal Turaev-Viro theory. Okay, so those three bullet points, 1, 2, and 3, are also essentially an outline for the rest of the talk. Before we jump in, I'll define what is a generalized tetrahedron. So a generalized tetrahedron is a tetrahedron in hyperbolic space with some of its vertices beyond the conformal boundary. You can make sense of this by thinking of hyperbolic space, thinking of the embedding space for hyperbolic space. And then what you do is anytime a vertex of the tetrahedron moves past the conformal boundary in embedding space, that vertex gets truncated on a geodesic surface, which is orthogonal to its neighbors. So you end up with this tetrahedron with cut off vertices, and each of the triangular faces of this shape meets the neighboring faces at a right angle. The core is then constructed by gluing these generalized tetrahedra on some of the faces. And the image that I had on the first slide was the was Nano Banana Gemini's artistic impression of what it looks like when you glue a bunch of these generalized tetrahedra together on some of their faces. Okay, so to split off the core and the asymptotic ends, we have to discuss what boundary conditions we're going to put on the core. And that's what we're going to do now to discuss. We'll discuss gravity on a finite region, where by finite, I compact Euclidean spacetime. The semi-classical saddle points will have finite volume. So the goal is to formulate the integral on a compact region with some consistent boundary conditions. The boundary is some union of Riemann surfaces. And the boundary we're going to choose is first we'll do a Pants decomposition of the boundary and then fix the lengths or the dihedral angles of the curves of the blue curves for that Pants decomposition. Those will become geodesics on the boundary. And with these boundary conditions, the boundary itself is a pleated surface with corners on geodesics. So a pleated surface is one where you have geodesic hyperplanes that are meeting at corners. So this is hard to draw for the full Riemann surface, like for M. But if we look locally near one of those blue curves, it just looks like there's a corner, a crease in the boundary. And then on that corner, we're fixing either the length L or the interior dihedral angle psi. The notation I'll use for these path integrals is the gravity path integral with fixed geodesic lengths is called Z sub L. The gravity path integral with fixed dihedral angles is called Z sub A for angles. And these two boundary conditions are related by a Laplace transform. You have to use a different action appropriate to the boundary condition, and you can go between them classically by the Legendre transform or in the path integral by this Laplace transform. Now, the first claim is that the fixed length path integral. So now we have these two different gravity path integrals we can talk about, fixed length and fixed angle. The first claim I want to make is that the fixed length path integral on the core calculates directly the OPE statistics. So let's consider, again, this case where you have a genus 2 boundary and a genus 3 boundary. In a CFT, the way you could calculate that is by expanding out the genus 2 partition function in conformal blocks and the genus 3 partition function in conformal blocks and get an expression that looks something like this. On the gravity side, this is this complicated geometry with a flare at each boundary and then a core. And the claim is that with the fixed length boundary condition, that cleanly separates out the various contributions to the CFT amplitude. Each pair of pants on the boundary corresponds to an insertion ofCijk. The core, the gray region, with fixed length boundary conditions, calculates the OPE statistics, so the statistics of theCijks. And then the flares, these asymptotic ends, contribute the factor of conformal blocks times C zeros. So the important thing is that with this boundary condition, it cleanly separates out the OP statistics from the rest, from the kinematic contribution of the conformal blocks.
Equivalently, shouldn't there be an integral over the lengths of the blue curves? Or are you suppressing that in the gravity path interval? You're integrating over the lengths of the blue curves, right?
Well, yeah. If you want to calculate at fixed moduli, then this is an integral over the length of the curves. But statement is just that the core at fixed lengths is the same. So without any integral, the core at fixed lengths is the statistics at fixed conformal weights. Equivalent way of saying this is that the fixed length path integral is equal to Virasoro TQFT squared with this normalization that I chose for the vertices where the theta graph is normalized to 1. So this fixed length path integral is the Virasoro TQFT amplitude squared. This is not really a new result. This is just restating the results of Virasoro TQFT authors in this language of gravity on a compact region with some boundary conditions. This identifies the boundary condition corresponding to their statement. Now that we've dealt with the asymptotic ends, the next step is to triangulate the core. Semi-classically, this can be done with fixed length boundary conditions. And at this point, we could talk about gluing together generalized tetrahedra with fixed length boundary conditions, and that would allow us to describe the core. However, it turns out that we'll find a much nicer exact answer by working at fixed angles. We'll find that the fixed angle path integral on the core is calculated by a different TQFT. That's the conformal Turaev-Viro theory. So the main result that we're working towards is this equation that says the fixed angle gravitational path integral on the core is equal to the amplitude of CTV, the conformal Turaev-Viro theory. The logic of the derivation, it would be nice to show this directly by doing the gravity path integral, but I won't do it that way. The logic that I'll follow is to start from the fixed length result, where the fixed length is equal to Virasoro TQFT squared, and then we'll take the modular S transform of both sides of this equation, and that'll give us the fixed angle related to CTV. All right, so now I'm going to define conformal Turaev-Viro theory, CTV. CTV is a topological theory that assigns amplitudes to trivalent graphs, similar to Virasoro TQFT. First, I'll describe it just as a TQFT without any reference to gravity. We'll come back to gravity in a bit. So denote the amplitude in this way as ZCTV, where ME is a closed three-manifold, E for embedding. This is different from the gravity manifold, which is why I called it ME. And gamma is a trivalent graph that's embedded in M sub E with edges labeled by conformal weights. The only conformal weights that we'll talk about are the conformal weights above the black hole threshold, which correspond. I'm using the Liouville labeling for conformal weights, where the Liouville momentum P is real. So to define the amplitude, we start by choosing a triangulation, T. Edges of the triangulation that belong to the graph are called external edges, and any other edges are called internal edges. To each tetrahedron in the triangulation, we assign a Virasoro 6J symbol. So the tetrahedron with edges, as shown in the picture, is the 6J symbol on the right. It's important that the 6J symbol is not quite the same one that arose when we talked about Virasoro TQFT. That one had P1, P2, P3 on the top. This one has P1, P2, P3 on the bottom. And that's related to dualizing the tetrahedron, replacing the vertices, swapping the faces and the vertices. But for now, this is just a definition. And now we can define the amplitude. So this is the definition of the CTV amplitude. There's a Virasoro 6J symbol for each tetrahedron. And then we integrate over the conformal weights on the internal edges. So the external edges are held fixed. Those are the labels on the original graph. And then we integrate over the conformal weights on the internal edges with the Carty density of states. So this is the definition. Some
Sorry,
comments
I
and
missed it. What
caveats
was
about.
what was gamma of P? Gamma of P. Let's see. ME is a closed three manifold.
Yeah, ME is say S3, and gamma of P is say a tetrahedron graph labeled by or any graph, but for example, a tetrahedron graph labeled by P, labeled by some fixed conformal weights.
And what's the distinction between internal and external edges?
So if ME is a complicated three manifold, then we would need to introduce some additional edges to triangulate it. Those are the internal edges,
Oh, I
and
see.
those need to get
The ones
integrated over.
the ones you're gluing.
Yeah.
Yeah, okay. And now, in a traditional way of presenting a topological field theory, you say what the amplitudes are from, linear transformations from ingoing to outgoing state spaces. So what's the state space? I mean, you've defined what to me looks like partition function of a closed manifold with a defect
Yeah.
in it.
Yeah.
And that's not the way a TFT is usually presented. So what's the state space on a Riemann surface?
Good.
And what's the data? I mean, what's the Bordism category you're defining as your domain? What's the data? What's the data of the three manifold exactly?
Good.
The
So
three manifold is it orientation, spin, what?
I'm using the original. I'm using that language that was used in the original Turaev-Viro, where the goal was to write down a topological invariant. Um, in Turaev-Viro for a compact group, the answers to all the questions that you're asking are known. There's the string net formalism that gives something like a Hilbert space for the Turaev-Viro theory. I haven't studied that for the Virasoro case, so I don't have an answer for that for the case that I'm studying here. I'm only going to tell you how to calculate the amplitude.
But I think, so following up on what Greg was asking, I think of Turaev-Viro associated to actually not a compact group, but a finite, so a finite number of generator fusion category, for example. And is there sort of a sense in which you could, just give us sort of the broad understanding of how the standard picture of the Turaev-Viro as a state sum for something that we would call the TQFT associated to a fusion category, how that's actually generalized here. I would imagine there are lots of subtleties with regards to the infinite number of topological defects that you have in your theory. Maybe that's related to some of the questions that Greg was asking too.
Yeah, I think
It's
that's
very related to what I'm asking. I mean, you have a continuously infinite number of
That's right.
simple objects.
Yeah. So I think that sort of these kind of infinities are things that in this generalized symmetry context haven't really been addressed. So it actually would be interesting to understand how precisely this can be done. And this seems like a setup where this is, at least it seems to be working, but it would also be nice to actually hear a little bit more about how it's constructed in terms of this TQFT data.
I agree with all that, but I haven't done it.
Okay.
So the Hilbert space, like this TQFT, it's going to have the same. Presumably, it's going to have similar issues to the Virasoro TQFT.
Mhm.
Like probably trying to define the Hilbert space on a sphere. There's going to be something. There's going to be some problem with that. I am going to mention these divergences in a second. Those are
Mhm.
important also in the way that I'm talking about it.
Mhm.
But as far as describing it that way, I don't know how to do it. I've only thought about calculating these amplitudes.
Mhm. Okay, thanks.
Um, okay, so this is a natural generalization of the standard derived Viro theory to a non-rational CFT. And as pointed out in these comments, there's a big difference, which is that in CTV, the total number of states is infinite. If we just add up all the states, that's integrating dp with the Cardy density, which is exponentially growing at large p. So this is the analog of this in ordinary Turaev-Viro theory would be the total quantum dimension, which is a finite number that shows up all over the place in the formulas for Turaev-Viro. So the fact that this is infinite introduces some crucial differences to the standard case. And we cannot just take the standard results of Turaev-Viro and apply them, assume that they carry over to CTV. Many things won't work. In particular, um, it restricts to certain triangulations. So in order for this amplitude that I wrote down to make sense, it should be a finite number that's independent of the triangulation. And that won't be true in general if I take an arbitrary triangulation of an arbitrary three manifold. Um, the when you go, so you need it to be invariant under changing the triangulation. You can get from any triangulation to any other triangulation in three dimensions by the 2-3 and the 1-4 Pachner move. So in CTV, there is a 2-3 Pachner move. So the 2-3 Pachner move um, relates in the language of well, this is the pentagon identity, and the pentagon identity is satisfied by the Virasoro 6J symbol. Um, so you're allowed to do the 2-3 move, and that keeps everything finite. But you can't do the 1-4 move. If you try to take if you try to take a tetrahedron and add a new vertex that divides it into four tetrahedra, then that'll introduce an infinity. So you're not allowed to retriangulate by adding vertices. Um, then there's a question of whether there's anything left in this theory. And there's certainly some things that are finite and make sense because I've calculated lots of examples, but I don't know what the precise class of three manifolds and triangulations is that's allowed. I'll talk about a couple examples where it does make sense. And the conjecture is that it makes sense, at least if the triangulation satisfies this topological condition that's written. Now, from the TQFT point of view, I think it seems very strange to restrict what manifolds and what triangulations you're allowed to study. Um, and in the literature on Teichmuller TQFT and um, the TQFTs surrounding it, I think that the way the topological field theorists would describe it is that it's not fully topological if you can't retriangulate. So that seems like a strange thing to do. But in the gravity interpretation, which we're coming to in a minute, this restriction is perfectly reasonable because adding vertices adds asymptotic ADS boundaries. And you would not expect from the gravity path integral that you can take some interior region, add a boundary in there, and then integrate over the boundary to glue things together. That feels like a very strange thing to do from the gravity path integral point of view. You would never expect that you should be allowed to do that. Whereas from the TQFT, it feels a little strange. But so from gravity, I think that's natural. Um, okay, let's look at an example. So one of the simplest amplitudes that we can calculate is this knotted handcuff graph. And we'll think about this as a graph embedded in S3. This graph embedded in S3 can be triangulated with a single tetrahedron. So if you take the tetrahedron on this slide and you glue together the two front faces and you glue together the two back faces, then you get an S3 with this graph embedded inside. In this case, there are no internal edges. All the edges of the triangulation are also edges of the graph. And therefore, the formula for the CTV amplitude is very simple. It's just the 6J symbol for this tetrahedron. So that's our answer for the amplitude in this one. Now, there's a well-known relationship between the standard Turaev-Viro theory and Chern-Simons for compact groups, which says that Turaev-Viro is Chern-Simons squared. So we anticipate something similar for our case. Um, the representations that are relevant here are the same as the representations, and the 6J symbol is the same as Virasoro TQFT. So we're expecting something like this that relates CTV to Virasoro TQFT. And it turns out that they're related by a modular S transform, satisfying this identity here. So let me say what's going in. On the right-hand side, there's a Virasoro TQFT amplitude squared. And then we're taking the modular S transform, or which is really just a Fourier transform because the S kernel is this cosine. So we do a Fourier transform of Virasoro TQFT squared, and that gives the CTV amplitude. I'm not going to go through the proof of this, but the idea of the proof is that the modular S transform replaces a triangulation by its dual spine. For each tetrahedron in the triangulation, which is like what's drawn here, there are dual edges that are associated to the spine, which is that shape inside, and the modular S transform replaces the edges by the dual edges. So a result that looks almost exactly like this boxed formula was already known for rational theories or for compact groups. And that was developed in the work of Roberts and Barrett and collaborators. The so the final formula looks very similar. The definitions are a little bit different, and the proof is different. So the non-trivial thing here, the new thing here is to show that you can rescale the definitions and do the proof a little bit differently in a way that avoids the factors of the total quantum dimension that showed up in the original way of doing it. So you have to show that you can go through all the same steps without encountering these infinite factors. And you can do that with some slight changes to the derivation. So it still goes through and you get the same identity at the end. So I'll look at another example now and show what this identity looks like. So this example is the tetrahedron graph. So the graph now is the tetrahedron graph, also embedded in S3. The Virasoro TQFT for the tetrahedron graph gives a 6J symbol with P1, P2, P3 on the top. So that's on the right-hand side of the identity. Virasoro TQFT squared is this 6J symbol squared. To calculate the CTV amplitude, first we have to triangulate the manifold. So you can triangulate this graph in S3 with two tetrahedra. You take the two tetrahedra and you glue them together on all of their faces. So two identical or reflected tetrahedra, and you glue them, you double it across the faces. Again, there are no internal edges. So the CTV amplitude is just the product of 6J symbols. The Virasoro is a product of 6J symbols with the 1, 2, and 3 on the top, and CTV is a product of 6J symbols with the rows swapped. So the general identity says that these should be related by an S transform, and the general identity in this case becomes this identity that says how the squared 6J symbol should change under the S transform. So this is just one example. In this case, you can prove this identity more directly by using more standard CFT transformations, although it's much easier to do in using the diagrammatic techniques of Virasoro TQFT. All right, now we're going to go back to 3D gravity and describe how this gets us back to the gravity amplitude. But maybe I'll pause here and see if there are questions before we get back to gravity. Okay. So first, we need to say what the manifold is on the gravity side. So CTV and Veroser TQFT were both defined for a graph gamma in a closed three-manifold M sub E. 3D gravity lives on the complement of the thickened graph. Okay, so if this picture is the knotted handcuff graph embedded in some three manifold like S3, then what we're going to do is we're going to thicken out the graph into a well, we're going to thicken it out, and then the complement of that M is a compact manifold with boundary, and we can impose fixed length or fixed angle boundary conditions on the meridians of the graph. Okay, so in the connection between the TQFT and the gravity amplitude, the TQFT was this graph embedded in M sub E, a closed manifold, and gravity, we're describing the gravity manifold as the complement M, where we cut out the graph and impose the boundary conditions on the meridians. In this example of the knotted handcuff, the on-shell geometry on the complement is a single generalized tetrahedra. It's tetrahedron. So remember when we did this example when we calculated the CTV amplitude for this example, we found the answer was a single 6J symbol coming from the single tetrahedron that you need. Sorry, in this case, I'm taking the embedding manifold to be S3. So in CTV, we found the single tetrahedron. When you go to gravity, you have to fatten out the graph. And when you fatten out the graph, that truncates the tetrahedron. So we started with one tetrahedron in CTV, then we fatten out the graph, and we get the truncated tetrahedron in gravity. So that's where these truncated tetrahedra are going to come from. But the truncated tetrahedra on the gravity side will correspond one-to-one with the tetrahedra that we had in CTV. So now we can prove this main result that relates to fixed angle amplitude to CTV. We'll start from the fixed length path integral. Recall we said that the fixed length path integral is the Virasoro TQFT squared, and that this is just the usual statement relating gravity to Virasoro TQFT restated on the compact region, where we normalize everything to get rid of the flares. Now we take the Fourier transform of both sides. On the gravity side, so there's a relationship between the conformal weights P and the lengths and the angles. So on the Virasoro TQFT side, the P's are proportional to the lengths. On the CTV side, the P's are proportional to I times the angles. Once you put all the I's in the right place, this Fourier transform on the gravity side is exactly the change of boundary conditions from fixed lengths to fixed angles. And then we invoke this identity on the TQFT side that the Fourier transform of Virasoro TQFT squared gives the Turaev-Viro theory. So this is the main result that we wanted. The fixed length path integral on the core is calculated by CTV. It's very easy now to take the semi-classical limit and to check that and to find the semi-classical geometries. This was not the case in the Virasoro TQFT or Chern-Simons type formalism. There it was hard to understand the semi-classical geometries. Here, I would say that Turaev-Viro is really the exact version of the metric formalism. And if you take the semi-classical limit of large central charge, then it just reduces term by term to the gravity path integral. The 6J symbol in the CTV amplitude gives you the action. Semi-classically, it gives you e to the minus action of a truncated tetrahedron, which is related to its volume. So there's a formula here that relates the 6J symbol to the volume of the truncated tetrahedron. And that ensures that everything works at the semi-classical level. But then once you've phrased it in Turaev-Viro, you get the exact answer. So we've succeeded in writing the gravity path integral in terms of a triangulation. We have some product of these 6J symbols and then integrated over the lengths of the internal edges. Um, there's also a nice recent paper by Jaffress and Wang where they give a direct interpretation of the right-hand side, where they interpreted this using the open or the BCFT version of 3D gravity and Virasoro TQFT. So in their way of thinking about it, each of these 6J symbols appearing on the right-hand side is really the gravity amplitude in the open case where you have some end of the world branes as well as edges. Okay, I'll wrap up with a few comments. So we evaluated the gravity path integral on a hyperbolic three-manifold by decomposing it into some natural geometric building blocks. With asymptotic ends, the flares accounted for the conformal blocks and C0 factors, and then the core that we obtained by generalized tetrahedra. The results agree with OP statistics calculated from Virasoro TQFT or the conformal bootstrap. So what next? I think one of the most interesting questions here is what happens, whether there's a corresponding story in three-dimensional de Sitter. And I think the answer is yes. In fact, the history here is sort of the other way around. So going back, this idea of using the 6J symbol to discretize a gravity path integral goes back to Ponzano and Regge. So in the Ponzano-Regge theory, they give a triangulation of three-dimensional gravity. Well, you can interpret their result as a triangulation of 3D gravity with a zero cosmological constant. And they're using the 6J symbols for SU2, ordinary SU2. Then Turaev and Viro introduced their invariant. And this is similar to Ponzano-Regge, but with the 6J symbols for some discrete representations of UQSL2. And it was quickly realized after the Turaev-Viro paper that their model could be viewed as a discretized theory of three-dimensional gravity with positive cosmological constant. In the original case, this is for the compact group, and so this theory has a finite total number of states, n, which in some ways sounds like the right answer. It could be that that's just the right answer in de Sitter. There are other reasons to believe that de Sitter, the quantum theory, should have a finite number of states. And then what I described, this conformal version of the Turaev-Viro that I described in this talk, is appropriate for negative cosmological constant. The group here is also UQSL2, but it's for a different continuous class of representations, which that don't have a classical limit in SL2. So in a way, the building blocks are similar, but it's the choice of representations that are different. There's also a difference in perspective that I've taken here. So the perspective in this talk is that we're not trying to do a microscopic discretization of gravity at the Planck scale. These are not like Planck-sized tetrahedra. What we're doing is we're just decomposing the path integral on geodesics in the semi-classical limit. So we're taking some manifold and cutting it into if it's a relatively simple topology, then there would be a relatively small number of large tetrahedra that chop up the path integral on geodesics. So it's sort of the point of view I was taking is that these are macroscopic tetrahedra, whereas I think in the literature on Ponzano-Regge and Turaev-Viro, the idea was that you would take this was a discretized toy model for gravity, and that it would just agree in the large n limit. So there's definitely some similarities there, but exactly how to interpret this in positive cosmological constant, I think is still not clear. I don't think we know, for example, how to do the exact gravity path integral in DS3 along the lines of what I've described in ADS. There are many other questions that this leaves open. I'm not going to go through all these. I'll just highlight the last two, which I think might be the most interesting. Number six, the off-shell topologies. As I mentioned at the beginning, the topological methods, both of them, the Virasoro TQFT and the Turaev-Viro method, so far we only understand how to do that on topologies that emit a hyperbolic metric. But we believe that the non-hyperbolic topologies are essential in the to get a sensible duality, to get a unitary, or to get a duality to an ensemble of unitary CFTs. And number seven, the CFT ensemble. Um, so we still don't have the analog, the complete analog of random matrix theory that would give us something like the microscopic definition of a random CFT that produces all of these statistics. What we have are some bootstrap methods that allow us to calculate certain contributions to that ensemble by plugging into the bootstrap equations. But we don't have a systematic way of really describing the details of that ensemble or matching them to the sum over topologies in 3D gravity. Okay, I'll stop there. Thanks.
Hey, thanks very much. Other questions? I certainly have one question to start with. Could you clarify again what you said? You were saying that you can't put your theory, this Turaev-Viro theory, on an arbitrary triangulation. So could you repeat what exactly you said there? What happens if you put it, if you change the triangulation or something? That seemed completely in contradiction with it being topological, but maybe I misunderstood something.
No, that's right. It's not, well, let's go back. Let's go back
Yeah,
so we have
it was
something
the
to stare at.
reference line.
Um, okay, so um, the statement is that not every triangulation will work. So that was correct. Like if we let's take, to be concrete, let's talk about this example of the knotted handcuff. So there we triangulated that was this one. So we triangulated this with a single tetrahedron. Now, you might try to divide that tetrahedron in four using this 4-1, or sorry, 1-4
Yes,
Pachner move where you add a vertex. Um,
what you just said there,
if,
yes. Mm-hmm.
so when you do that, you now have you've introduced four, well, I'd have
Yeah,
to think through
edges.
how many distinct one, but you've introduced some new edges. And so so now you have to do some integrals in the calculation of the amplitude. And those integrals, there's a divergent integral when you
Mm-hmm.
do that. So because when you turn this when you actually work through the calculation, you end up with a factor of n
Mm-hmm.
if you try to do the 1-4 move.
Mm-hmm.
So that doesn't work. You
I
can
think
retriangulate.
it might be a function of this earlier question that probably one should define some way of, making sense of these things by more from first principle so that these kind of things should be consistent. Is that maybe a way one could, right? I mean, it should be possible to change this triangulation because otherwise it seems to me um, it breaks some of the more fundamental things about this being topological. Um,
Well, in the gravity amplitude, um, you can do any triangulation. Well, I don't think it breaks the fact that it's topological. It breaks it's not acting like a standard TQFT, but it is giving you a amplitude that depends only on the topology.
hmm.
when it admits one of these triangulations, one of these allowed triangulations. Not every manifold will admit an allowed triangulation, and then the amplitude is ill-defined or maybe infinite on those
Mhm.
topologies. But when it admits one that's allowed, all of the allowed ones give the same answer because they can all be related by these 2-3 moves.
Mhm. Okay. But you agree that ideally there should be a more, or you could envision there being a generalization of Turaev-Viro to these, irrational kind of theories where you have a consistent set of rules where you're allowed to do these moves, and you have a well-defined prescription of how these kind of divergences are dealt with or regularized or something. Or you're just saying these are just inadmissible in terms of even, the theory is defined only on things that here are on the left and are not related to these by these 1-4 moves. So you
Yeah,
exclude, you're saying the theory is just ill-defined on such topologies or on such
um,
triangulations. Sorry.
yes, I'm saying for now at least it's ill-defined on those topologies.
But if
I
you
think
look
for
forward,
gravity,
right, I think you would want it to be well-defined, no?
well, if we were just doing TQFT, then yes, I think that's what people would say.
Mm.
But since I'm really trying to do gravity, I don't see any reason that we need those amplitudes. That
But it's not
um,
that when you study TQFTs, you can pick and choose what is okay about what you like about it. It should be sort of something that's consistent as a framework. I think you're using this TQFT and you had this relation of this TQFT being sort of directly related or calculating for you certain aspects of the gravitational theory. So I would have thought at least its first principle, it should be well defined and on its own, and then you can have an interpretation of it in the gravitational context. So I'm just trying to understand whether you expect there to be such a Turaev-Viro theory that is well defined. One just needs to more, work a little more to actually make this more precise, or you just don't expect it to exist at all.
well, I'm going to give an in-between answer. I don't. I think what should be well defined is the gravity amplitude on
Mm-hmm.
any topology.
Mm-hmm.
That's what should be well defined.
Mm-hmm.
And it might be zero on some topologies, but we do think that they're non-hyperbolic topologies where it's non-zero
I see.
and meaningful. So there should be so that should be well defined. That needs
Mm-hmm.
to give a number that needs to
Okay.
agree with CFT. Um, Anything beyond that, I don't know whether
Mm-hmm.
I don't think anything beyond that, I don't think we don't need, and maybe it's just impossible to
Mm-hmm.
define this version of Turaev-Viro. Um,
Okay. All right. And
Whether that
Greg has a question. Maybe we should have not made the point.
Yeah, I do have a question. So I'm just a comment on the discussion you just had with Sakura. I'm wondering if two-dimensional Yang Mills at area 0 is a good analogy.
hmm,
So that is a partially defined topological field theory. The amplitude is infinite on the sphere. The Hilbert space is infinite dimensional, but sorry, the amplitude is infinite on the sphere and the torus at 0 area, but it's well defined on hyperbolic manifolds, hyperbolic Riemann surfaces, as a topological field theory. So um, I wonder. I'm just wondering if people have known that forever, but I'm wondering if that's a good analogy.
hmm.
Um, that's just a remark. I had two questions. One, why do you call it conformal Turaev-Viro?
Well, because it's related to two copies of Virasoro. So I think the word I think I'm thinking of the word conformal to mean two copies of Virasoro.
I was expecting when I saw the title of the talk, I was expecting to hear about Liouville and maybe the conformal anomaly and integration over the Weyl mode and stuff like that. But
Well, there is a relation to that. There,
yeah,
there, yeah, there is the like if the when you do these calculations, when you do these wormhole calculations in the metric formalism, you end up reducing the action of 3D gravity to a Liouville action. So
uh,
there is a connection to Liouville, which I didn't describe. But
is there an
conformal to
analog
me
of
just meant
conformal? If there's is there an analog of conformal Turaev-Viro for finite for compact groups or for a
no.
vector fusion category? No. Okay.
No, by the word conformal just meant the Turaev-Viro. All I meant by that was the Turaev-Viro theory that corresponds to two copies of Virasoro.
Okay. Um, and then I also this pertains to your last open problem. So you had this asymptotic expansion. I think I asked a question when you wrote the dot plus dot dot dot. Well, that's my first question. So if you're summing over topologies and the number of three manifolds, the number of hyperbolic three manifolds of volume V is expected to grow like V factorial. So in your, at the very beginning, you wrote the formula for the leading term in the statistics, and then you wrote plus dot dot dot. That plus dot 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 includes a sum over three manifolds, right? Or
Yes.
maybe only the three manifolds for which CTV is defined. I'm not sure. Is it a sum over all three
I
manifolds or?
it's a sum. Well, I don't know if it's all, but it's not over just the hyperbolic. It's not over just the ones where CTV is well defined.
I said,
There are there there almost certainly are contributions on manifolds where CTV does not make sense,
okay,
or at
but
least CTV
let's
as they've written it.
okay, but let's consider the subsum over the hyperbolic manifolds.
Yeah.
Now, okay, so then the number of hyperbolic manifolds with curvature normalized to -1 of volume V grows like V factorial. So you've got a pretty divergent series there if you're really seriously going to incorporate the sum over topologies,
I
right?
think it's even worse than that because there are accumulation points in the volume spectrum at finite.
There's that issue too. There's that issue too, right? Um,
So the
Steve
accumulation,
Carloff. Steve Carloff wrote a beautiful paper right after Witten's paper on interpreting gravity as Chern-Simons, where he pointed out that this is a big problem.
hmm,
But but anyway, so I mean, so there's this sum, and I think the best you can hope is that it's asymptotic.
agreed. Yeah.
Oh,
This,
okay, so the idea is to find what is a non-perturbative completion of that asymptotic series. Is that when you say you want to understand the exact statistics or the
that's
non-perturbative completion
yes,
of
that's right.
okay,
That's right.
okay. So I guess one thing is to understand better in what sense it's asymptotic, right?
Yeah. Yeah.
Because of the problems we just
Uh-huh.
mentioned.
Uh-huh. Yeah, although there are problems that are potentially there's a step you can take that's potentially easier than getting the full non-perturbative answer, which is just to be able to write the statistics as coming from the moments of something.
Okay,
There's no like this method calculates some things that I'm calling statistics, but there's no guarantee that they satisfy the properties of the moments of a positive distribution.
right. I see.
And so one needs to show that and check that and ideally find the distribution.
Got it. Okay. Thanks, Tom. Beautiful
But
talk.
the comments about the non-perturbative, I agree. I think it's similar in JT that it's non-perturbative, and then it's really the finite n, it's the finite size random matrix theory that's the full non-perturbative definition.
Right. Just like in the 1991 versions.
Yes.
Okay, great. Are there any other questions? I don't see any hands up. So let's actually thank Tom again for a nice talk. I will stop the recording.